All right, guys. Well, can everybody see me and hear me out there okay? I'm still coming in clear today. Um, all right. In that case, I am going to go ahead and get started. It is about 1 o'clock. And welcome back for the second class. I always get nervous after the first class. Will anybody come back again after the first round? And you guys are still here. So that's a good thing for me, especially. And just a couple quick announcements here, and then we'll get right into some additional math review today. Um, First of all, I've started to have a little trickle of some students stopping by to say hello in my office hours, and that's great. And I just want to encourage the rest of you, if you haven't had a chance to stop by and say hello, feel free to do that. We're going to be doing Zoom next week as well, so these first 2 weeks. But if you are just waiting to meet me in person, you won't have to wait too long. I will be back in February, and that won't be too far from now. Um, Also, just a quick reminder that there is a homework assignment due tomorrow night at midnight, essentially. I know a lot of people have already made some good headway on that, but if you do have any questions about it, especially as we're trying to kind of get used to a new semester, maybe you just want to make sure you're formatting things correctly and so on and so forth. Yeah, feel free to stop by and chat with me. I'll be around tonight. I'll be around after class today, although I would prefer not to have any long conversations right after class because I have another class in an hour. And because of the time difference, I'm going to need to like eat something. It would be a lot better for me for those of you who are willing to stop by during my evening hours tonight. That would work great. I get done with my last class at 8 o'clock, and then I'll be in my office hours from 8 until 9, and then again from 10:15 until midnight. So quite a few hours later on this evening that would be really good. Alternatively, you can catch me tomorrow. I am going to probably change my hours tomorrow again because of the time difference. The way I have them set up right now is going to be right in the middle of my dinner time in Nebraska time. So I will probably shift my hours tomorrow. In fact, let me do that now. So this is just for these first 2 Fridays, but um, my Friday office hour, I'm going to go from 7 until 10 tomorrow night. I think what it says in the syllabus is that I'm going to go from 3 to 5 and then from 9 to 11. This will be a little bit better. It'll hit the sweet spot of my evening between my dinner hour and my bedtime. So let's go with that just for tomorrow and also for the next Friday. I don't always have office hours on Friday anyway, but I should be available tomorrow. So if you don't get a chance to talk to me today and you're working on the homework tomorrow and you get stuck on anything, feel free to jump into Zoom with me anytime between 7 and 10 p.m. You can also shoot me emails. I do respond to email as best as I can whenever I can. And I can also try to help you that way. So whatever works best for you, just let me know. So that's the first homework assignment coming up for tomorrow. And then we'll have another assignment due next week also on Friday. So um, I think by the time we get through today's class, you might be able to start looking at some of that as well. But at least for the material for this first homework, we're going to pretty much be good to go here today. So any questions, guys? Everybody with me out there? Okay, great. Let me just make sure I've got 22 people here. I see that you're here. I don't know if you've been added to Canvas yet. You talked to me after class on Tuesday, but I don't actually have your email address, Cal State Fullerton email address. That was the main thing I need from you. Please send me an email from your Cal State Fullerton email address if you'd like to get me to add you to Canvas so you can see what the homework is and everything. All right. Otherwise, I think everybody who I see here right now is enrolled in the class and good to go. So that's good news. That's good news. We've had plenty of room to get everybody in. All right, well, take a breath here. On Tuesday, we talked about sets. This was just a review, obviously, of set theory from Math 280 and a little bit of baby proofs to kind of get in the rhythm of how I like to write things down and kind of what you might be aiming for a little bit as you're writing up your own proofs. Today, what I want to do is talk about functions, which of course take great advantage of sets in their own right. And so it's a natural next step. And obviously functions are going to be the backbone and the core of a lot of mathematics, and real analysis is no exception. So this is in section 1.3. Again, I consider this to be mostly review, but we'll go ahead and start with the definition of a function here again, and then we'll do some examples and talk about some related concepts as well. As always, guys, let me know if you're not able to read anything on my board. I do have my chat window open, and so I'll be glad to keep an eye on that, and you can also use your microphone if that's easier. But let's write down the definition of a function. I think this is definition 1.7 in the book. So here is what it says. We're going to start with two sets, capital X and capital Y. So let capital X and capital Y be sets. These are going to ultimately be the domain and the codomain of the function. Okay? So then a function, right, which is written this way, little f, colon, and then x with an arrow pointing towards y, right? This is the way we would denote a function. It's inputs and outputs. This is a rule. This is a rule that assigns. This is a rule that assigns to each little x belonging to the set capital X a unique output. I'll call it an element, a unique element, which we write as f of x, which is an element of capital Y. So to each input to the function, there should be only one output, right? We can't take an input and send it to two different outputs. That would not be a function. And then just as long as we're here, let me just add a little bit more here. In this definition that I'm writing down, capital X is called the domain, and capital Y is the codomain of the function little f. So there's always a domain and a codomain for a function as such. Okay. Be careful not to confuse the codomain with what's called the range of the function. I'm just trying to pin myself a little bit better here on my screen so I can see what I'm doing. Sorry. There we go. Okay, so do not confuse the codomain of a function with the range of the function. The range of a function is just all of the possible outputs. So I'll write that down as well. The subset, we talked about subsets last time. The subset, which is denoted f of capital X, and this consists of all of the set of the little f of x's. So you take every possible element of the domain and you just evaluate the function and you form that set, right? The set of all of these f of x's, that's denoted f of capital X. And this is the range. This is called the range of f. Okay, it's obviously a subset of y. So I can just make that as an additional note here that the range of f, which is f of capital X, is a subset of y. So I'm using that subset notation that we introduced on Tuesday to represent that. Is everybody able to see this okay? Okay, good. It's pretty readable. That's great. So yeah, I always think of functions kind of visually like this. You have an input, capital X, and you have an output set, capital Y. So you have these two sets, and then the function f is going to take elements, which I'll represent by little dots here, on the input side and map them to the output side, right? So you could imagine arrows that take these elements and map them from one side to the other. So I'm just doing some random set of arrows here to give you kind of a little bit of an idea what that might look like. So this is an example of a function, just a visual picture of what it might look like, right? So you've got 5 or 6 inputs here, and that means there's arrows, 5 or 6 arrows going onto the output side. Notice that the range of this function, the way I've drawn it, only has what? 1, 2, 3, 4 elements in it, right? So in this case, this would be what's called a proper subset of y. So I'm writing that with a little slash through my underline symbol here. Is that clear to everybody? I put a little slash under this thing. Let me make that a little more obvious, right? So in this picture, for this example, the range of the function is a proper subset of the codomain. It's not the entire codomain in this case. It could be the entire codomain, but it doesn't have to be. Okay, actually, that kind of leads me to another concept that you guys are probably familiar with that I thought maybe I should talk about, which is the idea of onto and one-to-one functions. Does that sound familiar from Math 280? Yeah, I think that should be something you've seen before. Let me come back over here, and I'm just going to add those definitions as well to our notes here. Okay, so we'll talk about this for just a minute. So more definitions, guys. Sorry, a lot of definitions to kind of start things off this semester. That's pretty much par for the course for math, right? So the definition here is that a function, I'll call it f again, going from x to y, is onto, or sometimes there's another word that you'll hear people use a lot, which is the word surjective. So the function is surjective, or in other words, it is onto or surjective if the range of the function is equal to the entire codomain y. So that is an equal sign right here. If the range of the function is the entire codomain y, then we call this thing onto. By the way, the range is also sometimes called the image of the function. I forgot to mention that earlier. Let me put a little asterisk here next to my definition of the range. And I'm just going to add that right down here. This is also called the image of f. So another equally interchangeable word. You might hear me use it from time to time. I might call the range the image. Means the exact same thing. Guys, as you can see, the big deal about a function being onto is that everything in y is realizable as f of something, right? So this is an equality here. It's always a subset, right? F of x is always a subset of y. The issue is it actually equal to y? So to check if a function is onto, we're going to practice this in a minute, but the way you would check it is you would take an arbitrary element out of capital Y and try to figure out how to write it as f of something, right? That's how you prove onto. You take something out of the codomain, some arbitrary dot in Y over here, and you try to write it as f of something if possible. That would be the way to prove that a function is onto. Okay? Everybody with me so far? Questions? So far, so good. Okay, good. Well, going right along with onto, the other sort of companion concept is the idea of a one-to-one function. So I might as well write down this definition as well. This one's a little more element-based. So what we can say is that a function, I'll just add it right here, a function f going from x to y is one-to-one. 1-to-1, and there's another word that we sometimes will see for that. It's also referred to as an injective function. So a 1-to-1 function is also called injective if, so this one, as I said, it's a little more of a clumsy definition, the way we actually write this down. But the way it would look on paper is if x1 does not equal x2, then f of x1 does not equal f of x2. Okay, so this is a way to conceptually think about it, is that different inputs have to be mapped under the function to different outputs, right? So that's what 1-to-1 means. You'll notice over here in my little visual picture that I drew, this function is not 1-to-1 because I can take, for example, let me highlight this x value, that could be x1, and then I might also take this x value, which could be x2, and I can even take a third one, x3. There's 3 different x's, which I've tried to highlight with these thicker dots here, guys. F is mapping them all to the same output, even though those 3 points are obviously 3 different points. So here you have different inputs being collapsed to the same output. That violates this definition over here, which says that no. For a 1-to-1 function, if you start with 2 different points, they have to be mapped to 2 different points. Right. That's the definition of 1-to-1. Okay, and then putting these together, we get the idea. I'll put one more definition here that's also along the same lines, which is the idea of a bijection, right? So a function f, one more time, a function f going from x to y is a bijection. It is a bijection if, so a bijection is just a surjection and an injection. So if f is both 1-to-1 and onto. 1-to-1, I'm just drawing that as 1-1 here. It's just a little less writing for me if I do that. But it has to be both 1-to-1 and onto. So that would be a bijection. Is everybody pretty familiar with these terms? Seen these before, I hope anyway. If that's all good with you guys, then maybe I'll write down an example of this, and we can talk about it here. So let's put an example down. But I do have my chat window open, and I also am welcoming you guys to use your microphone if you do have any questions about any of these definitions. But let's make an example. Let's define f to go from the real numbers to the real numbers. And that is telling me what the inputs and the outputs are. Since this is real analysis, it kind of makes sense that I'm going to use real numbers for some of my domains and codomains throughout the semester. And here's the function. I'm going to define f of x to be equal to the square root of x squared plus 1. So we're going to take that as our example. And then what I'm going to ask here down below is f 1-to-1 onto both or neither? Kind of a 4-part multiple choice question here, right? 4 options. I want to know whether it's 1-to-1 onto both or neither. You cannot tell the answer to that question only by looking at the domain and the codomain. So obviously here we have the same domain as we do codomain, but that doesn't mean that the function will be onto or 1-to-1. We have to actually think about these definitions here a little bit. Okay, so let's see if we can do that. Let's check. Well, I'm going to check if it's 1-to-1, and I'm going to also check if it's onto. We're gonna do both of those things, right? So let's talk about this a little bit. How can we check if this is 1-to-1? So to do that, I look back. Here's the definition right here, guys. 1-to-1 Now, the way I phrased the definition, you have these not equal to conditions. That's not very easy to work with, as much as if you had like phrased it using equal signs. Would we be able to rephrase this box using equal signs instead of not equal to signs? So x1 does not equal x2 implies f of x1 does not equal f of x2. That can be logically rephrased in what's called a contrapositive format. And the contrapositive format is that, so this could be rewritten. I should have left myself a little more room here. This can be rewritten. I'm going to just squeeze it right here, guys. This can be rewritten. F of x1 equals f of x2 implies x1 equals x2. So these are absolutely the same. So I just wanted to squeeze that in. I like to intuitively think about the definition. The way I originally wrote it is better for intuition in my view. But for proofs, which is what I'm going to do right now, I'm going to prove that this function is one-to-one, hopefully. We'll see. I like to use the rephrased contrapositive expression of what one-to-one means, because when you rephrase it, you have equal signs everywhere, right? So I can assume, if I'm checking one-to-one, guys, I'm going to assume this part. I'm going to assume that f of the first point equals f of the second point. Now, I don't like to use a lot of subscripts, so I'm going to actually, instead of x1 and x2, I'm going to use x and y here. So let's do that. Let's assume that f of x is equal to f of y, and I would like to check whether or not that implies that x equals y. We're going to just see if that's true or not. Okay, so this would mean that the square root of x squared plus 1 is equal to the square root of y squared plus 1, right? So we would just start off by recognizing that much. And now I'm just going to do some basic algebra, right? So I can square both sides of this equation, right? So if I square both sides, I'll get x squared plus 1 equals y squared plus 1. And then I'm going to subtract 1 from both sides. All right, so I get x squared equals y squared. What I need to get, if this is a one-to-one function, is I need to end up with x equal to y. Do I get that here? If x squared equals y squared, does that mean that x equals y?
No.
Careful. Yeah, we can always take a vote in the, I'll figure out how to do a, somehow I can do a poll in Zoom, I think. Anyway, I won't bother with that for this. In this case, no, right? If you, for example, 3 squared is the same as -3 squared. They're both equal to 9, but 3 and -3 are not the same. This does not imply that x equals y. And so the answer here on the one-to-one is a big no. It is not going to be one-to-one. You actually could have proven that without doing all of this abstract algebra calculation. If you wanted to, you could just prove that with specific numbers, as I just kind of suggested, right? What you could do, if you now realize, oh, the answer here is supposed to be no, right? What would be a good justification? And guys, on my exams in 350, I will often be asking for examples and counterexamples. This is a counterexample. I'm going to write down a counterexample to show that this statement is false. This function is not one-to-one, as it turns out. So the way you would do it is you could just say, look, f of 3, right, which is equal, by the way, to the square root of 10, is the same thing as f of -3. Two different inputs giving me the same output. And so actually, this would be all you would really have needed to write down to justify it. Again, I'm kind of putting on my Math 280 hat right now. This is like if you want to disprove a statement, all you need is one example, right? Just one example of it. So that would be fine. But the fact of the matter is sometimes you don't know if the statement is going to be true or not when you start. So you're like, I don't know whether this is true or not. So you might start off with this chicken scratch calculation. I talked to you guys on Tuesday about how I think it's a good idea to work out your ideas on scratch paper first. So maybe this would be on your scratch paper, and then your actual solution to justify whether f is 1-to-1 or not would be to say no, and here's the counterexample. And this is actually all you really need to show me. Okay, but anyway, it's always good to know where that intuition came from. This scratch work would have been kind of behind the scenes helping us to figure that out. Okay, so it's not 1-to-1. While I'm erasing, take a look at that. Make sure you're comfortable with it. And if you got a question about it, let me know.
Yeah, Professor.
Yeah, I'm here.
I don't know if it's just me, but I can't really see the bottom of the whiteboard.
Oh, the very bottom of.
Yeah, there we go.
Can you see it better now?
Yeah, we can see it now.
Okay, sorry about that, man. Okay, so the function is not 1-to-1. Let's check the onto part. Now, again, before we just launch into trying to write out a polished discussion of this issue, it might help us to either write down some scratch work or even to just think about it for a minute. Do we think that every possible real number, right? The codomain here is R. Do we think that every real number could show up as an output of this function? Brian, you're shaking your head no. What's the matter? What's going to go wrong, do you think?
It doesn't account for any negative numbers because there's a square
Negative
root.
numbers. Yeah, I love that. See, when you take the square root of something, you have to get a positive number. If I ask you what is the square root of 9, the answer is 3. It's not plus or minus 3. It is literally 3. That's the convention of what this square root function means, is that you are taking the positive value. So yeah, as Brian said, it does not account for negative numbers. So we already kind of have an idea that this is a no. And so let's get right to the heart of the matter and let's justify it. What we could do is we could say -1 is not an element of f of the real numbers. And you could pick any negative number that you wanted here. You could pick -5, you could pick -22, you could pick anything that's negative, and it will not be an output. And that's pretty much clear just from the fact that this function just has square roots of numbers on the right-hand side. So this one is actually neither, guys. This one is not 1-to-1, and is also not onto. Okay, good little practice there. You want to try one more practice problem, or do you kind of have the idea here? Pretty good? All right. I'll leave it at that for now. We can always come back and practice a little bit more later. But there is another concept here that I want to review for a minute. And this one I do notice when I teach this class tends to give people more trouble. And that is namely that there's the idea of the image and the pre-image of a set inside of a function. So I want to talk for a minute about that. So let's title this little discussion images and pre-images. Right, okay, so what we could do here, guys, is we could let f, which is a function from x to y, I'll just say let that be a function. And then what I'm going to do is I'm going to let A be any subset of x. Any subset of x. So on the input side, we can take a subset of the domain. And what we can do is we can talk about, well, actually, yeah, so then the image of A is the following thing. It's literally just f of capital A. It's f of capital A. And so this is referring to the set of little f of little a such that little a is in capital A. So just like the range of a function, this is a subset of y. Again, this is a subset of y, but this time we're not taking f of every input. We're only looking at f of elements that came from capital A. So this will be some subset of capital Y. It's called the image of A. And we can do this for any set that we want, right? Capital A could be any subset of X. All right. Similarly, I'll just leave a little space and then add a second part to this. Let's let capital B be a subset of Y. So we can start with something that is inside of the codomain of the function. And in this case, I'm going to talk about something called the preimage. So then the preimage of capital B is, okay, so here's the image right here. I'm going to circle that one. And then the preimage is written with this f to the -1 notation. We have to be really careful here. When we see a -1 used like an exponent, a lot of times people will think that I'm talking about an inverse. I'm not assuming that this function has an inverse at all. This is literally a notation, and granted, I don't think it's the world's best notation, but it's just a notation that mathematicians have adopted. So the preimage of B, what is that going to be? That's going to be a set of x's in capital X such that, right, if we take f of x, this becomes an element of capital B. And this one is inside of X, right? This one is a subset of X. So this is the preimage of B, okay? I'll go ahead and put a box around this as well. It's a pretty important thing for us to be familiar with. The preimage of B. Notice that the B is a subset of Y to begin with. The preimage pulls it back to become a subset of X, which is the opposite of how the image works, where you start with something as a subset of X and push it forward into the codomain Y. So we're doing push forwards and pull backs, pushing forward and pulling back. And you are going to see some examples of this in the homework, and we're going to do some group work on it as well. Try to choose notations when you're grabbing elements out of these sets. Try to choose notations that make good sense for your setup. For example, if I wanted to grab an element out of the preimage of B, I would not want to call it little y, because little y, I mean, it wouldn't be wrong to call it little y, but little y makes me think it lives in capital Y, when in fact, no, if I'm grabbing something in the preimage of B, it lives in capital X. So I would want to use a notation that supports that kind of helps me to understand that. Ayushi, do you have your hand up there?
Yeah, I had a question.
Please, yeah.
So what if the set in the set B, there is the function like it does not exist if there's no input from X to, like, if there is an element in B.
If there so if the elements of X, if none of them get mapped into B at all, then the preimage of B would just be the empty set. We talked about this empty set on Tuesday, right? It might be that there are no elements of X that land inside of capital B, and that would be perfectly reasonable to have the empty set as an answer. Does that make sense? Yeah? Okay, great. Let's do a quick example. We've already got this function on the board over here, so I thought maybe we could just play with an example for a minute. So the example I wanted to do here is with f above, so above meaning the function we were using a minute ago, Let's compute a couple of things just to kind of practice this. Let's compute, let's start with the image of the interval from -3 to -1. And I'm gonna, just to make it a little bit fun, I'm gonna use a half open interval here. So let's go from -3 to -1, but open on the -3 side using a parentheses and closed with a bracket on the -1 side. And let's see if we can calculate f of that. So what this means, I'm using the function that's over here. I'm gonna plug in all of the inputs that are from this interval into that function, and I'm gonna collect all of the outputs, right? And I'm gonna see if I can figure out what that would be. So let's think about it for a minute. Like if I plug in -1, right? If I plug in -1 into my function, I'll get the square root of 2. If I plug in 0, I'll get the square root of 1, which is 1. You know, I can plug in anything here. I technically cannot plug in -3 because -3 is excluded from this open side of this interval here. But just for pretend, if I did plug in -3, we said earlier that that would have given us the square root of 10. But technically square root of 10 is not allowed here. So I'm wondering if anybody has a proposal for what the image of this interval, this is my capital A right here in my definition. So I'm taking f of all of those elements. What would be maybe helpful for us here is, can we figure out what's the smallest output and what's the biggest output so we can kind of make an interval out of them? It's kind of what I'm getting at here. Anybody have any thoughts? You can put them in the chat if you're not sure, or even if you are sure, you can, or use your microphone. I think the biggest output that you could get, if we included -3, would have been the square root of 10. But see, I'm not allowed to use the square root of 10, so I'm going to imagine that my answer is going to go all the way up to the square root of 10, but not including the square root of 10. And then it's sort of like, well, what's the smallest thing we could get? If I want to come up with the smallest possible output to this function, like it seems to me that the smallest type of x that you would want to use would be x equals 0, right? And John's got it in the chat for us here, right? If I put in 0 for x, I get, oh, actually, John doesn't quite have the same thing in the chat that I'm thinking of. If I put in 0 for x, I actually get the square root of 1, which is 1. Which is actually a little bit smaller than the square root of 2. The square root of 2 would be correct for the value of f of -1, but this is a little tricky because the smallest value that I can get out of this function on this interval actually does not occur at the endpoint. It occurs at 0. Wait a minute, I'm not allowed to use 0. I'm not allowed to use 0. For some reason I was thinking this is -3 to 1. Yeah, I'm not allowed to use 0, so I was trying to plug in 0 over there by mistake. I should not be doing that. I can only plug in numbers in this interval, right? So if I do that and I plug in -1, I absolutely do get the square root of 2. So John had it right. I should never have doubted him. Now, if I had said, maybe just now you've got me kind of curious, just as a quick follow-up here. Just for a quick follow-up. What is f of the interval from -3 to 1? So if instead of stopping at -1, if we stopped at 1, then again, the largest output that we could get would be the square root of 10. But this time, this is what my brain was doing. I wanted to plug in 0, and now I can do that. And if I plug in 0 for x into this function, I get 1. And that would be included in that interval then. Okay, so that's perfectly reasonable. One of the things we're going to learn this semester, guys, is that if you use a so-called continuous function and you look at the image of an interval, you'll always get another interval. So that's kind of confirmed here. This is a continuous function. You probably know that from your calculus background. And so if I plug in an interval, I'm gonna spit out an interval as well, and we see that here. Okay, so far, that's the image on an example for this function that we've just been looking at. Let's look at another example using a pre-image. Okay, so for the pre-image, let's do another example. So with f as above, let's compute the pre-image of the open interval from 5 to infinity. The pre-image of the open interval from 5 to infinity. So I'm using the same function again. I've managed to keep it on the board here for a little bit of time. Let's look at this this one right here. So now I'm asking which inputs to this function would give me outputs that are bigger than 5, right? And keep in mind that your outputs are clearly expressed by the formula, right? The square root of x squared plus 1. So the question is just going to be, what would be the inputs that would give me that output? Can anybody suggest how I would figure this out? So remember, we're kind of going in reverse now. We're starting with the outputs, which are these square root of x squared plus 1s. And we're trying to pull back to the x's, the inputs to the function. The pre-image of a set is back on the x side, the inputs to the function. So the way that you would tackle this, guys, is you would set your f of x to be in this interval from 5 to infinity. Okay, so we would imagine that this is the case. Now, of course, that just means that the square root of x squared plus 1, which is what f of x is, needs to be greater than 5. Right, needs to be greater than 5. So what I can do with that is try to solve this for x now, right? If I could solve this for x, I would square both sides. All right, then I would subtract 1. So x squared needs to be greater than 24, is basically what it's going to take, right? As long as x squared is greater than 24, we should be good. And that tells me that x should be greater than the square root of 24, is that right? Is that the only thing that we would take into account? I see some people who are recognizing that because we have squared the x here, we need to be careful because there would be some negative values of x, which after squaring them would be bigger than the square would be bigger than 24. So the other possibility is x could be less than negative the square root of 24. You have to be real careful about that. And so this actually gives me 2 intervals of the real line. And I would recommend, so my answer now, I would recommend expressing this answer as a union of 2 intervals. So I would probably write this as minus infinity going to minus the square root of 24, union the square root of 24 going to infinity. This would be a nice way to write the answer. You know, of course, it's not the only thing you could write. I mean, you could also write the answer as real numbers minus the closed interval from negative radical 24 to radical 24. We could just take the whole real number line and remove that central section of the number line that we need to exclude from the pre-image. Does this make some sense? Either one of those ways of writing the answer would be fine. Let me give you one more follow-up here. So much of what we do in 350, guys, is abstract proofs. So I hope you enjoy some of these examples. We won't be seeing examples all that often, but I think examples are still important even when you're doing theoretical math to help you get some intuition behind what's going on. So don't be surprised if I do some more of this kind of stuff as we go forward. Quick little follow-up here. Let's figure out what would be, so compute. One more pre-image here for us to practice. Let's compute the pre-image of the interval from, well, let's go back to the one we were using before, -3 to -1. But we have to be really careful here, guys, because now I'm talking about the pre-image of that interval, which has absolutely no connection to the image of that same interval that we just did a couple minutes ago. So here I'm asking which inputs to this function f, which I've still got right here on the board, which inputs would produce outputs in that range from -3 to -1. I'm putting this question up here kind of for Ayushi as well, because we talked about this a minute ago. And in the chat, Ayushi's kind of got a good idea here, which is that you cannot get a negative output to this function, right? This function only outputs positive numbers. And so the answer here, it's kind of a trick question. The answer is empty set. There's nothing, right? You cannot plug something into this function and get an output that's in that interval. And so, yeah, that would be the way you could look at that one. Okay. Questions on that? All right. So I've talked about images. I've talked about pre-images. I've talked about one-to-one, onto, bijections. These are all good things for us to play around with. Let's see, before we take a break today, let's do a abstract proof now. Let's do something a little more theoretical that involves some of these concepts we've just been talking about. So I'm going to come back over here and we'll practice one more example before we take a little 10-minute break. So what the example is going to be, still a little bit cold in this room I'm in, so erasing is kind of an adventure. Thank you for bearing with me. I hope this isn't too boring. Once I get back there in person, I'll be jumping around a lot more than I do in this room. I have to be a little more under control in here. Okay, so I've got that cleared off, at least decently for the moment. Here, I can just finish this off. Okay, so yeah, let's do a quick example. So let's do another example, and then we'll take a short break. So let's do this. Let's let f from x to y be a function. We'll start with a function again. And I'm going to let s and t be subsets of y. And what I would like to do is prove that if I take the pre-image of S union T, that this is equal to the pre-image of S union the pre-image of T. Okay, so this is a more theoretical example that we can practice on here a little bit. Sorry, let me make sure you can see that whole thing. Right, so in other words, what this is saying, guys, is that pre-images, they kind of respect unions, right? They play nice with unions. If I have a union of sets, I can take the pre-image of that union by doing the individual pre-images and then taking the union after that. So this is, again, guys, both sides of this equal sign are subsets of X, right? The pre-images live over here on the X side. So let's start we're gonna prove these set equalities by doing subsets both ways. We learned how to do this we reviewed how to do this on Tuesday. And so now that's what I'm gonna try and do. And I'm gonna start off right now. I'm gonna do something that's not necessarily wrong, but that's maybe not a good idea. And so don't write this down yet. I just want you to watch this and tell me what I'm doing wrong, okay? So here we go. I'm gonna start off, let Y be an element of the preimage of S union T. How do you like that? It's not wrong, but the problem is that I'm treating this Y as if it's gonna be an input to the function. F of Y is gonna live in that union, but the function doesn't take elements of Y as inputs, right? The elements of Y should be the outputs. So it would be better, I'm now going to write down something much better. It would be better to call it X. Just so we don't get confused. It's more for our own benefit than anything that's required here, but I would prefer to call it X. Now, because I don't have a huge board here behind me, I've had to kind of get rid of these definitions of preimages, but you've got them there in your notes. This is where I'm starting. I'm picking an element on the left side, right? And I want to prove that it lives on the right side. So what does this mean according to the definition of preimage? If we go back in the notes and we look at the definition of the preimage, what this means, if something is in the preimage of a set, it just means that if we take F of that element, it lands in that set. So what it means here in this case would be that F of X is in S union T. Okay? And that kind of gives me two cases, right? So, case one, when we talked about this on Tuesday, when we have unions involved, that creates cases for us. If we're assuming that F of X is in the union of S and T, then the first case would be that F of X is in S, and then we'll do a second case in a minute where we'll assume that, so I should write the word assume here. Assume that F of X is in S, and then down here we'll assume that F of X is in T, and kind of go like this. Everybody so far so good? Okay. I can't see everybody all at the same time because I'm not keeping my Zoom window open for that. So if anybody's out there, especially if you don't have your camera on, I can't see you. If anybody's out there kind of not sure of something, be sure to let me know, okay? But I've got two cases here. F of X is either in S or it is in T. Let's imagine that F of X is in S. What do you suppose I'm gonna say next in that first case? And of course, I want to look at what I'm trying to come up with here. I'm trying to show that X lives over on the right-hand side. Yeah? What does this mean?
X is in the preimage of S.
There we go. X would be in the preimage of S. I love it. Exactly right. X is an element of the preimage of S. Great. Just by definition of preimage. Okay, so X would be in the preimage of S. So then, if it's in the preimage of S, then of course it's in the union of that with anything else. So I can go ahead and conclude that then X is in the preimage of S union the preimage of T. Awesome. Which is what I wanted, right? I want to get that conclusion. Whether X actually belongs to the preimage of T or not doesn't matter to me, right? If I know that it lives in the preimage of S right here, then of course we can union that with anything to make the set bigger, and X will still live there. Okay? Now I have a feeling some of you are out there writing down case 2. I want to point out though that we will find times in this class where writing the same basic argument multiple times is going to drive us nuts. It's basically going to change all the S's to T's and so on, and it's more or less no new ideas. And so when you have a case that is similar to a case you've already done, you can just use that. You can shortcut this. So I'm just going to say similar to case one. The only thing I have to call, and so we'll put a check mark there and I won't write that one down. The only thing is, be careful not to abuse that option, because if the sets S and T, maybe they had slightly different properties. If S and T had different properties, then maybe whatever we were saying in case one wouldn't be applicable to case two. So that's one issue to keep in mind. But in this case, the S and the T are arbitrary. There's no more assumptions about one of them than the other. And so a similar to case one reason would be totally fine. Okay, and that finishes our proof of the first half of this. Okay, so let's go back and go the other direction now. Let's assume for the converse direction down here that X is an element of the preimage of S union the preimage of T. Again, do not call that an inverse, please. Use the word preimage when you see this kind of notation. All right, so then this means that X is in the preimage of S, or X is in the preimage of T. That's what the union stands for, and that, of course, gives us two cases again. Okay, so case one, let's assume that X is an element of the preimage of S. That's one possibility. Can somebody immediately translate that for me? If X is an element of the preimage of S, what am I going to say next? Almost without thinking about it.
F of X is an X.
Yeah, exactly. Okay, I heard several people say it. Yeah, absolutely. So then this means that F of X is an element of S. Now, what do I really want to prove? I really want to prove that F of X is in S union T, because that's what the left-hand side has, S union T. But if F of X is in S, then of course, that implies immediately, we know how unions work, based on what we did on Tuesday, that F of X is in S union T. In fact, F of X is in S union anything we want to write down. Okay, great. And so then from there, we can unwrap that one more time. That means that X is in the preimage of S union T. Awesome. So there's your conclusion, and that's what we wanted. That's what we wanted to get in this case. All right, and then case two. Case two would be to assume that X is in the preimage of T. And what am I going to say on this proof? It's similar, exactly. So this is similar. I'll just say similar to case one. Awesome. And that's the end of that little proof. Does this make some sense? Now, guys, on Tuesday, I made a little comment that students who are really on their A game in this class, people who are really trying to be up to par with everything, are going to ask a lot of questions. They might be rhetorical questions. They might be just things you're thinking in your own mind. But I want to give you an example of that here. One question that you might naturally ask yourself right now is, would this work for arbitrary unions? Here I've done a union of two sets. The question that you might have in your mind is, well, would the same idea be true if this was an arbitrary union? And it turns out that it will work. And I actually wanted to let you guys know. So this problem is actually in one of the group work handouts that's in Canvas. Group works, we're going to start doing those when I come back to campus, but they will not be graded in this class, but they're just chances for us to practice the material. So this one's in there, and I'm going to recommend that, yeah, if you have some time and you want to, try to see if you can prove it for arbitrary unions. It turns out it works. There's nothing special about only using two sets here. So if we had a union of 3 sets or 4 sets or 5 sets, or that whole thing we did on Tuesday using an index set, and creating an arbitrary union, this same proof will still work. It'll just have to be written a little bit differently with the notation, but the idea is the same. Can anybody think of another rhetorical question that I might be asking myself right now, but aside from just, does this work for arbitrary unions? Would there be something else that would be like a question that would be coming up in our heads at this point? Lila's got it in the chat for us. Yeah, intersections, right? Would it be true for intersections? A really good question. It turns out, guys, that it is actually also going to work for intersections. So if anybody's interested, you can take this proof and in your spare time, see if you can write up what the proof would look like for intersections. It's also going to be true. And in fact, it's going to be true for arbitrary intersections. So I'm going to just make a little remark to that effect so that you have it in your notes and maybe you'll come back to it in a time that's convenient for you to kind of play with a little bit. So just as a quick remark, this example can be extended to arbitrary unions and intersections. So you can do it for any of those, which is kind of cool. So I'll just say this is a nice exercise. This is not technically a homework problem, but when I write something like that down, it just means I'm inviting you to play with it a little bit in your spare time. Okay. While I'm at it, I'm just going to, well, actually, so I have another question. Would there be any other extensions of this that we might think of besides arbitrariness and besides going from unions to intersections? Would there be any other kind of other things we might want to consider while we're kind of thinking about these things? I have one. I always have one. What about images instead of pre-images? So, here I'm talking about how it works so nicely. Pre-images play nice with unions, with intersections, and so on. Another question is, what about images? And I do have a comment for you about that. It turns out that images do not behave so nicely. Specifically, so I'll just point out this example does not extend to images. So we've got a nice example about pre-images, but it turns out that for images, it does not work nearly so nicely. And Ayushi's got a point in the chat as well about taking set differences. You might remember from Tuesday that I sort of talked about how a set difference, you can think of a set difference as being expressible using unions and intersections, right? So, like A minus B, that's the same thing as what? We could take that to be, well, here's the picture of it. Put B right here, put A right here. So A minus B is right here. You can kind of think of that as A intersected with what's called the complement of B. The complement of B, I know I haven't really officially defined what the complement is, but everything outside of B, if you intersect that with A, you would get this ring right here. And because pre-images behave nicely with respect to intersections, they will also play nice with respect to set differences. So you're absolutely right. Ayusha, you've got a nice proposal in the chat, which I would invite anybody to try to write down the proof of. It's a good practice problem. But yeah, this stuff does not work so well for images. It turns out that unless the function has some extra properties, like maybe if it's one-to-one, I think if it's one-to-one, then the intersections do work with respect to images. But in general, it's not the case, and we could give counterexamples, right? Yeah, so actually, let's take a 10-minute break. See if, let me just write this down. During the break, if you want to take your break, of course, go right ahead. I'm going to do that. But if you don't need a break and you just want to have a little fun for a minute, see if you can make an example that shows that f of s intersect t is not the same thing as f of s intersect f of t. So I'll just put this as an example. And when we come back after 10 minutes, we'll see if we can write down an example together. But let's take a break until about 2:15. If you need to get a stretch your legs, get some water or whatever, this is a good time to do that. And then we'll come back and we'll play with this example I just threw on the board in a few minutes. All right, see you soon. Guys, if you're somewhere out there within the sound of my voice, I'm going to be starting up in about 1 minute. So just to give you a heads up, in 1 minute, we're going to get rolling again here. By the way, guys, you might have noticed that there are 2 Scott Annans in this Zoom session. That's because I have both my laptop and my phone here. I think that my phone takes maybe better video. I'm not sure, but I just thought to help you guys out, I would sort of double my presence in this Zoom call. But what I just realized is that the 2 Scott Annans have 2 different chats. So I was only seeing I was seeing the chat from the one that's let's see, where am I here? From the one that's over here, I'm kind of waving at it. So I might have missed a couple of chat messages going to my phone because my phone's a little small. So I've got this chat window open over here on my other Scott Annan. So anyway, sorry about the confusion with that. I'm co-host of this Zoom session with myself in the other version. Makes sense, right?
Split personality.
I have a double personality and you are seeing double, and it doesn't mean there's anything wrong with your eyes.
You're just larger than life, Dr. Annan.
At least for now. We'll see what happens in a couple weeks. Anyway, yeah, so let's go ahead and I don't know if you guys were trying to think of a counterexample during the break or not. I did see one person sent me an idea. Keep in mind that to give a counterexample to this statement, you have to tell me what is F, what is X, what is Y, what is S, what is T, what is S intersect T, and what is F of all of those things. So it's not just a one quick breath thing. You actually have to write down a bunch of stuff to really provide me with a counterexample. Does somebody want to give me an example of just what the function is that they think we might be able to use to give a counterexample here? And there's lots of right answers. I always like to be helpful, so I'll do the easy part. Let's use a function from R to R. And okay, John's got an idea in the chat. Let's play with that for a second. What if we try to let f of x be equal to x squared? All right, so that's a perfectly good function, and it's pretty easy for us to play with. And now I've got to come up with a couple of sets. And wondering if anybody has, maybe somebody besides John. I already know, John, I already know you know this one. But this is good. Does anybody have a suggestion for what we might choose for S and T to kind of disprove this example? And maybe I'll give you a little bit of a hint as to how to think about it. If you choose your 2 sets to have an empty intersection, so they have no common elements, then the left-hand side would just be empty. But you could set this up so that the f of s and the f of t, even if s and t have no common elements, f of s and f of t might have common elements, right? So let's just play with that. What if I just let f be, I don't know, the set of 1, and maybe t could be the set of 2, something like that. So in this case, what we have is, the intersection is empty. And if the intersection is empty, then of course, f of the empty set, if we don't have anything to plug into the function, then when we take f of that, we don't have anything to get for outputs. So that would be empty. All right, well, with that in mind, let's look at what we would get though if we did f of s and if we did f of t. To calculate f of s, now guys, we're pushing forward. So we're applying the function to these sets. So in the case of f of s, I just have to calculate f of 1. Well, f of 1 is just 1, because 1 squared is 1. And if I do the same thing with t, well, that means I'm going to plug in 2. I plug 2 into the function, and 2 squared is 4. So we would get 4 here. And is this what we want? Not if we're trying to get a counterexample, it isn't. Guys, I did this on purpose to show you that sometimes you're not going to think of exactly the right thing to do immediately, right? And you might try to create an example and it really just doesn't work the way you want it to work yet. But by writing this down, it might help inspire us as to how we could tweak it so that it will work. So is there something I might want to change about the example, either S or T or something like that, that would help me to kind of see what I'm hoping for is that the intersection of f of s and f of t is not empty. And right now it would have been empty because there's nothing in common between 1 and 4. So what could I tweak? How could I tweak it to make this work now?
You like 1, -1?
Yeah, exactly. Change the t to be the set of -1. I like that idea. So let's just erase a little bit here, because if we change the t to be -1, and now we do f of -1, we get 1 again. Okay, and so in this case, the intersection of those two sets is just 1, and so these do not agree. And so that's our counterexample then, right? That gives us a nice counterexample. The f of s intersects t does not agree with f of s intersected with f of t. Does that make some sense? Now, I'm going to go back to that quizzical approach of asking questions. Okay, so we've realized now that images do not play nice with intersections, right? But we might ask ourselves what could be salvaged from this, right? Clearly, we're not going to be able to say that these two sets are equal to each other. But as it turns out, okay, I'm going to try to share my screen right now, but I'm going to be sharing my laptop screen, not my phone screen. Remember, there's 2 Scott Annans in here. Let me see if I hope this is going to work. I'm just not the best with technology. I'm going to try to show you something. Let's see if this is coming up for you. What I've tried to put on the screen, guys, is a handout that's in Canvas. And I mentioned this a moment ago that I have these group works in here. Once we're back in person, face-to-face, I'll probably try to have us do some of these group works in class together. But look at the very first problem number 1 right here. What it says is that, well, first of all, it's talking about arbitrary collections of sets, but it's talking about images using intersections, which is exactly what we just looked at on my example a moment ago. And notice what it's saying there. Prove that one of them is a subset of the other. Okay, so even though we are not able to prove equality under this intersection, images of intersections property, we can still salvage subset. All right. So I'm not going to have us do problem number 1 right now, but over the weekend, if you have a little spare time, you might try it. Don't forget that the solutions to these group work problems can be found in the Canvas folder as well. So I'll have solutions to the proofs as well. Ayushi is asking me, well, what's the difference between doing this with images versus doing it with pre-images? It's really kind of a deep question, isn't it? I think the point is that these are just very different operations, and the way functions work, pushing forward versus pulling back are 2 very different they have different characteristics. And so we can't draw conclusions from one of them based on the other. This would not be a place where we could just say, oh, it's similar, and just kind of use that reasoning here. You do notice I have problem number 2 there on that group work. That's the one we did before the break. So I've already kind of done that group work with you. And then there's problem 3 is one that is just based on sets alone. And it's a arbitrary family of sets. And we're looking at how they behave with respect to Cartesian products. So the moral of the story here, guys, the big theme here is that we've talked about images, pre-images, unions and intersections, and so on and so forth. And the questions are just very natural. What properties can we prove involving those concepts, and which ones can we not prove? So the ones that are in the group work here, obviously you're proving those, but obviously some things are not always true as well. So just keep that in mind a little bit. By the way, here's another thing. If you want to salvage an equal sign right here, okay, we just said a moment ago that we have a counterexample. But if you want to salvage this statement and make it true, let's put this as another remark. I'm just going to make this as a remark that f of s intersect t equals f of s intersect f of t is true if we need an extra assumption. Does anybody have a wild guess what the assumption might be? What property we would need to add to this whole statement to make it work? Somebody sent me a message that as long as one of them was a subset of the other, and that's absolutely true. If S was a subset of T, then we definitely could salvage the equality here. Is there something we could do to salvage it without changing what S and T are at all? Ooh, Crystal sent me you guys are sending me private messages. Feel free to just send them to everyone. That way we can all kind of glance at what we're saying. What Crystal said is, well, what if we restricted X to be positive? And certainly for this kind of function, that would definitely do it. The issue here is that we have both positives and negatives. And so we get like f of 1 is the same as f of negative 1. Right? So if we restricted the domain, that would work. In general, Ayushi's picked up exactly what I was going to say. The way to salvage this is that it will be true if f is 1 to 1. That turns out to be the magic property that makes it work. So again, I'm going to leave this as an exercise. This is not homework specifically for you to turn in. But for anybody who's going above and beyond and doing all these rhetorical questions and trying to think about what things we could do, that's a nice exercise. Prove that if f is 1 to 1, then this preservation of intersections will be true. And so f will respect intersections as long as it's 1 to 1. So I'll leave that for now for you guys to play with. Maybe at some point in the future, we'll have a chance to discuss that in more detail. Okay? Any other follow-up comments, questions, remarks about all this? Just the big theme here is get real familiar with 1 to 1 and onto, with unions and intersections, and with images and pre-images, and kind of how they all play together with each other. This is kind of a great way to kind of get warmed up for the semester, I think. And some of them are in the homework, some of them are in the group work, but you can make up others of these questions to ask yourself as well. And do they work for arbitrary sets, or do I have to be limited to just 2 sets? That's another good thing to kind of play around with a little bit. I think what I'd like to do though now, guys, with a little bit of time here that we have left, is I would like to talk about how 1 to 1 and onto relate to the cardinalities of the sets. I haven't been talking so much about cardinality today, but that's actually some place where we can make some good ground. So I'm just going to say relationship between one-to-one onto and cardinality. Remember, guys, cardinality is just referring to the size of the set. So the cardinality of a set is just how many elements are in that set. And there are some facts that are pretty easy to believe and establish here. And I thought I might just write some of these down for you. Let's start off by just assuming for a moment, and I guess I'm going to continue to use X and Y here. Let's assume that X and Y are both finite. When I say that the cardinality is less than infinity, that just means that we're talking about finite sets. There's like a limit to how many numbers that you have or how many elements you have in your set. If we assume that the sets are finite, then if f going from x to y, so this is a function from x to y, if it is one-to-one, if the function is one-to-one, then the size of x has to be less than or equal to the size of y. So most of this is going to be kind of in the form of common sense. Can you guys all read that? This just says size of x less than or equal to the size of y. Is that clear enough? Try to pull this in here, make sure. Okay. So the way I like to intuitively think about this statement, guys, is in the sort of the contrapositive rephrasing of it. If y was smaller than x, okay, I'm going to give you the reason without writing it down, if that's okay, because this is a fairly basic thing. But if y was smaller than x, contrapositive, right? If y was smaller than x, then you would be forced by the pigeonhole principle, Amber, that there would have to be two different inputs that would be mapping to the same output, right? Anybody want to take combinatorics next semester or has taken it last semester?
Litzy said she wants to take it again.
Yay! Okay. Well, anyway, yeah. So one of the things I talk about in Math 471 is the pigeonhole principle, which is that if you have more arrows coming out of the domain of the function than you have boxes to map those arrows into, then there has to be two different inputs going to the same output. I mean, if you need to visualize it, it's not hard. Just imagine for a minute that, again, imagine that y was smaller than x. Now you've got three arrows coming out of x, but there's only two places for them to go. So just by common sense, I'm going to say, if I may, two of those arrows have to go to the same point. They have to merge to the same point, and that violates one-to-one. So if a function is one-to-one, you can't have this kind of a picture, if that makes any sense. Okay, great. So that's the first fact. I'm not proving it rigorously, but I think intuitively it's probably pretty clear. The second one is also pretty clear. If the function f is onto, so if you have a function going from x to y, and if it's onto, well, in order for that to be possible, then the size of x has to be greater than or equal to the size of y. So this just turns the inequality around. And now you know that there has to be a bigger domain than codomain. And then finally, we'll put those two things together. If f from x to y is a bijection, so bijection, as you'll recall, just means it's both one-to-one and onto. And if I look at the first two facts, if my function is both one-to-one and onto, the only way that could happen is then if x is the same size as y, same number of elements, right? These facts are usually used in contrapositive form, right? So if x is bigger than y, then the function can't be one-to-one. If x is smaller than y, then it can't be onto. And just more broadly, if the two sets have different sizes, you're not going to have a bijection. It's just that easy. Okay, so that's kind of clear. Right. Let me write down a fourth fact that's kind of maybe a little bit separate from the first three, but still related. And this one just says, well, if f, which is a function from x to y, is a function and the size of x is equal to the size of y, would that guarantee that you have a bijection between that f is a bijection? I'm really just probing the converse of statement 3. If I have a function and the two sets have the same size to begin with, would that automatically mean that the function must have been 1-to-1 and onto? And the turn.
Would you need a little bit more than that, Dr. Annan? Wouldn't you have to say that one of them is a subset?
Yeah, you're right. This is not true, and I see in the chat some people are kind of hesitating about this one. Yeah, it's not going to be true that you can assume that f is a bijection. You're right. What can we say? Well, what we can say here is that then f will be 1-to-1 if and only if f is onto. Okay, so what we're really saying here is that our function has to be both or neither in this case. So if the function fails to be 1-to-1, then without even checking it, we know that it would fail to be onto. Okay, so that's kind of what I'm saying. Now, none of this would really apply to the example we were doing earlier over here because the real numbers is not finite. But you can kind of imagine that if we were looking at finite sets over here, then the minute that we prove that f is not 1-to-1, we would know automatically that it's also not onto. Okay, so that's kind of the spirit of that result. Okay, so it's both or neither. In other words, that sort of 4-part multiple choice would be either both or neither. Okay, great. Any questions about any of these? These are for finite sets only. In a minute, we're gonna start expanding our horizons and start thinking about infinite sets for our domains and codomains again. Because after all, a lot of the functions in this class are gonna be defined on the real numbers or on some interval, and those are infinite. So this, in some ways, although these are very nice results here, they're not particularly helpful all the time for the functions we're going to see in calculus. So what we're going to do is try to talk more about cardinality even for infinite sets, okay? And I don't quite know, I really like our book. I mentioned on Tuesday, I'm a big fan of our book, but one thing that doesn't make as much sense to me as I would like is that they postpone talking about cardinality until the very end of chapter 2. And so what you're going to see me doing here, guys, is I'm actually going to jump to the last part of chapter 2 because I want to talk about that now, since we're kind of talking about these ideas of bijections and injections and surjections. I'm going to talk about cardinality next, and then we'll go backwards to the first part of chapter 2. So what I'm going to do, again, I didn't really prove any of this, but that's partially because we're not going to be using this as much. I want to get into a new section of the book here, which is really focused on cardinality in full. And we're going to cover this section first, and then later we'll go back to the first part of chapter 2. By the way, I'm pretty much drawing a line on chapter 1 right now. We've kind of done a review. We've talked about basic set theory, basic function theory. I've given you a few things to think about, obviously, with this review, but I'm ready to kind of move into maybe something that not all of you have seen before, which are some of these more generic concepts on cardinality. So before, and we're not going to we only have like 10 minutes left. I'm just going to start this today, and then next week we'll pick back up with it. Does anybody have any questions though so far? Because it's kind of a good place to take a breath for a second. So far, so good. Okay. Yeah, so I guess the warning here as I kind of start, I'm gonna jump to section 2.4. The warning here, I actually will write it down for you. My little warning here is that these above ideas, so the above facts, don't hold if the sizes of x and y are infinite. So if we have infinite sets in front of us, then if we want to test if a function is a bijection, for example, we can't just figure out whether they have the same size or not. It gets a little bit tricky. Let me just give you an example of this. So just to kind of drive this home a little bit, let's suppose that capital X is the integers. Okay, so just to give you an example, and let's suppose that capital Y is the set of the even integers only. So I'll write it in words. Sometimes you'll see this written as 2z. It's kind of if you've taken Math 302, some kind of an abstract algebra class, they would probably write the even integers as 2z. So these are both infinite sets, right? You could say that they're both the size of infinity here, right? And then I'm going to define a function now. Let's define f from x to y via, and I'm just going to make a very easy function. I'm just going to let f of x equals 2x. Okay, so we can certainly do that, and turns out that that is a bijection. This function is a bijection. So here, f is a bijection, and it's not hard to prove, right, that this function is one-to-one and that it's onto. If we assume that f of x equals f of y, then yes, x will equal y. And if we start with any element of the codomain, any even integer, we can sort of cut it in half, and that'll be a preimage for that element. So this is a bijection for sure. And so what we would have to conclude somehow is that then the sizes of the two sets are the same, right? So the kind of the punchline is that then x and y have, I'm going to put this in quotes, the same cardinality. Size is kind of my casual word for it. Even though they don't look like they should have the same size. One of them is a subset, a proper subset of the other one. And yet somehow I'm now telling you that, oh, they have the same number of elements, right? Like you can actually make a one-to-one correspondence between the integers and the even integers, right? There's an actual bijection there. So that's kind of a little bit of weirdness. I wouldn't want to say that there's the same number of elements in x and y, but strictly speaking, that's kind of what we're saying here. There's a bijection between these sets. Okay, so let's put down a little bit of notation here and terminology to kind of wrap up the class for today, and then we'll come back to this again next week. This gets a little slippery, this concept of cardinality. So I want to treat it with some care, but it's a neat subject that I don't think gets covered normally in any of the other classes that we have. So here's a definition for you. And for whatever reason, the book decides to kind of go away from x and y, and they start using a and b to talk about their sets. So I'm going to do that here as well, just to be consistent. Two sets, a and b, so capital A and capital B, have the same cardinality. Same cardinality. I hope that's legible for you guys. I'm trying to write on a board that's not totally firmed into my wall. So my parents didn't want me to pound a bunch of nails in the wall, you can understand. So A and B have the same cardinality, and this will be written, there's a notation for this. A with a twiddle over to B, so we're gonna be seeing this notation. If they have the same cardinality, right? A and B have the same cardinality, if there exists a bijection F from A to B. If there is a bijection from A to B. Okay, fantastic. So this is a better notion for us to kind of use going forward, instead of talking about the number of elements and comparing, well, how many elements are in one set versus another. What we're gonna be doing more often is asking, is there a bijection, right? Is there a bijection between those sets? And so there's some easy things that I think we could all agree on pretty quickly in just 5 minutes that I have here, and I'm just gonna write these down now to kind of get us comfortable with this a little bit. The first fact, again, there's gonna be 3 facts here. Every set is the same cardinality as itself, so this is not surprising. This is for every set, capital A. A will be in bijection with itself. This is sometimes referred to as a reflexive property. So the twiddle notation is reflexive. Everybody twiddles themselves, right? And I'm pretty sure you could come up with the bijection. Technically, we have to create this bijection from the set to itself. Just in brackets here, I'll just explain it, even though I know you guys could do this if I stranded you on a desert island and you had to come up with this before you could get off the island, right? You would probably define your function from A to A via just taking an element little a, and what would you do with it? Where would you have your function send it? Just do it, I can't hear you, Ayusha, but I think you're mouthing it. You just send it to itself, right? You would just like basically send f of A goes to A. All right, and it's easy to check that that's one-to-one and onto, right? So that's not hard. So that's kind of the first fact. The second one is that if A has the same cardinality as B, well then, not surprisingly, B will have the same cardinality as A, right? And so there's not a lot to that either. If you have a bijection that takes inputs from A and maps them to outputs in B, then you can just take that bijection and reverse the roles of the inputs and the outputs, turn the arrows back around again, and that will be a bijection going in reverse, right? Going the opposite direction. So I won't write all of that down. This is called the symmetric property. So that's the symmetric property. And then finally, the third one, did anybody learn somewhere that when you compose 2 bijections together, you get another bijection? That's all I'm gonna use right now. If A is in bijection with B, so if A twiddles B, and if B twiddles C, right? Then A twiddles C. And this is called, some of you may have heard this word before, it is called the transitive property. So this is transitive. So if there's a bijection going from A to B, maybe it's F, and then maybe you have another bijection G that goes from B to C. Well, then if you just compose those bijections together, you'll get a composition, which is a bijection directly from A to C. Okay, so I'm talking out loud sort of through the proofs of these. mostly because I'm running out of time. We could easily write this down. But all three of these things are true. The same cardinality concept is reflexive, it's symmetric, and it's transitive. But I want to leave you, since I have 1 minute left, I want to leave you with some slightly more interesting examples that I'm not going to prove right now, but we'll come back next week and see if, well, you're going to have 5 days to think about these. Because these are maybe not so intuitive. For example, the real numbers are in bijection with the positive real numbers. How about that? So, in other words, I can make a bijection between two sets that look like they're totally different sizes, right? The set on the side, on the right-hand side is a subset, a really smaller subset of the real numbers, and yet it has the same cardinality, right? So that's one kind of neat thing. Another one that we have is that, well, we can go from 0 infinity, and if we want to, we can just knock that down to the interval from 1 to infinity. And it turns out that those are in bijection with each other, right? And then one more here. What about 1 to infinity in bijection with just the interval from 0 to 1? Turns out that those are also the same cardinality. And actually, so then if you use your, you notice what I'm doing here? I've got A twiddles B, B twiddles C, C twiddles D. And so guess what, guys? A would twiddle D by the transitive property. So the real numbers are in bijection with just the open interval 0 to 1. But Hung Jun has asked me a question in the chat, which is a very good point. Do all infinite sets have the same cardinality? It turns out they do not. The real numbers are not in bijection with the rational numbers. You cannot do that. And therefore any subset of the rational numbers, like the integers, would not be the same size or the same cardinality as the real numbers. So here's another homework for you for the next 5 days. Again, you don't have to do this for homework. See if you can come up with the bijections here. See if you can come up with the functions that sort of demonstrate that these sets do have the same cardinality. Next week, we'll prove some of these. I'll try to convince you that the real numbers and rational numbers are not in bijection, that you cannot do that. And we'll look at some more examples of this as well. So this is section 2.4. If you're looking for any of you trying to get ahead over the weekend, feel free to jump ahead in the book a little bit to cover that. That's all I've got for you for today, though. I know you've got to go. Thank you for being here. If you've got questions, I'll hang around for a couple minutes, but my preference would be, in this particular case, I'll be around my office hours this evening, starting at 8 o'clock. I'd love to talk to you then as well. So thanks for a great day, everybody. Anybody have any last questions before we go? All right. I'll see you from Nebraska next time around. And John, I can answer your question in a minute. All right. Let me once again try to stop recording this. Figured out how to do it this time.